Thank you very much, Dr. Strassmeyer. I've been very pleased and honored and happy to get to experience the very warm welcome I've received here in Potsdam. It's a great pleasure to be here with you at the Leibniz colleague and also at the Astrophysical Observatory, Astrophysical Institute at Potsdam. It's been a wonderful trip for me so far. You're very fine people, and I'm a happy person. Thank you for the very fine birthday gift. I am here to talk to you about particularly the search for extraterrestrial life. And we must keep in mind two things. There's primitive life, which was probably much more abundant in the universe, and there's intelligent life, which is probably not as abundant, but yet is probably more interesting because that is what most people are particularly interested in. And I'm going to show you how the probabilities of the existence of life and the ways in which we search for it depend very much on astrophysics and physics in general, which is why the title of my talk is as it is. Now, I want to start out by talking about where we might find life, how common might it be in the universe, because this gives us guidance as to how difficult our search may be and what procedures will work best to find that life. To start off with, what do we mean by life? When we talk about life, at present we have to talk about life as we know it. The life of Earth, the way it works, its chemistry, its history of evolution, these things which we know. We wish we knew the same sort of information for other forms of life in the universe, but we don't. And so much of what we do in thinking about extraterrestrial life is based on life as we know it, life on Earth. And so when we think about searching for life in space, we sort of think about searching for other Earths, like the nice image you see here. Well, what is life as we know it? It's basically very simple. It's organic compounds, carbon-based compounds, interacting primarily in a solvent known as water. Fortunately, a solvent which is very common on our planet. So what it takes to make life is water, organic compounds, and one other thing, which is energy. And here on Earth, all of the energy of life comes primarily, at least to begin with, from our sun. And of course, it's converted by plants into food and things like that. But basically, the source of energy is the sun. And so when we look out into space and consider where else there might be life, we always have in mind, perhaps in too limited a way, that what we're really searching for is places with water, energy, and organic compounds. Now, when we say water, we mean liquid water. We don't know of ways of making life in solid water, that is ice, or in the gaseous phase. And so we look for places in the cosmos where the temperatures are right for liquid water to exist. And this has led to the concepts you see here, which is that around each star there is a thick shell, which you see here, within which bodies will have on the surface a temperature suitable for liquid water. Now you see here three different kinds of stars. In the astronomers' rather awkward nomenclature, an F-type star is a very massive, bright star. A G-type star is a medium-sized star, and in fact our sun is one of those. But in fact most of the stars in our galaxy, the Milky Way, are a third type of star called the M-type star, which is a very faint star. Its brightness is only a few percent, at best, that of the sun. Now what comes of this is that when a star is very bright, of course, you can have temperatures high enough to support liquid water far from the star, and those temperatures will continue until you're so far from the star that the temperatures fall to the freezing point of water. And so that is how we determine this zone within which habitable planets might exist. For a star like our sun, somewhat fainter, the habitable zone is more narrow. And for the M-type star, it's this little tiny donut you see here. Now, historically, astronomers have looked at the picture just like this, and they've said, all right, about the only place we might find life in the universe is around the G-type stars and the F-type stars. But the M stars are very faint. The potential zone of habitability is very small, and it seems unlikely that there would be planets in that zone. Well, that concept, as with many of the concepts with regard to life in the universe, has slowly disintegrated and fallen away as we have learned more about the ways in which planets can be, in a way, constructed in a different way so that they can produce habitat suitable for life. Now, there's another problem with the M star, by the way, and that is that little donut is so close to the star that even if a planet were in it, we would expect it to keep one face towards the star, just as our moon keeps one face to the Earth, and as a result, one side would be extremely hot, the other extremely cold. The cold side would freeze the atmosphere out, and the planet would become uninhabitable. But we'll see that all of that is changing. So we have this basic picture, and what we do is take a star, and we compute the size of the habitable zone, and we see what planets might be in that habitable zone. If we do that for the Earth, we get a picture as you see here. Here we see the distance from the sun in astronomical units, which is the distance of the Earth to the sun. And here are the various masses of stars, and their types are shown here. Here's the G star, here's the M star, here's the F star. And here's our solar system, here at the height of one solar mass. And here are the planets of the solar system in their proper distance from the sun. And here's the habitable zone, which of course gets closer to the left here as we consider the M stars. It moves outwards for the hotter stars. And we see then at the range of the G stars from the sun that the habitable zone is only about so wide. And we look at that, in a way it's both encouraging because the Earth is in it, so that's good news. The Earth is habitable, which we actually always have suspected. But the planet Venus is just a little bit inside the habitable zone, probably too hot, and Mars is just about outside the habitable zone, too cold. Now, this is all based on a very oversimplified idea, and that is that the surface of planets is controlled strictly by the amount of sunlight that falls on them. The sunlight falls on the surface, it warms it up. As it warms, the surface re-radiates by Planck radiation until the temperature of the surface stabilizes at such a temperature that the radiated energy just balances the incoming solar energy. And that is how we determine the temperatures of the planets and whether they should be in the habitable zone. Well, in that simple picture, as you'll see here, there's perhaps only one habitable planet in the solar system. And that picture I just gave you is an old one. It goes back about 20 years. And as I'm about to tell you, there have been a lot of very good surprises since, and all in a way increasing the number of planets that are habitable. And in particular, we will see that our solar system is very revealing. In fact, I like to call this the lessons from the solar system, things in the solar system itself which tells us about phenomena which will greatly increase the habitable zone in our galaxy and in the vicinity of various stars. Well, the first lesson from the solar system, whoops, going the wrong way, comes from this planet, which is the planet Venus. In principle, a planet almost identical to the Earth. It's the same size, the same mass. One major difference, though, and that is its atmosphere, rather than being one atmospheric pressure, is more like 100 times the atmospheric pressure of the Earth and is mostly carbon dioxide. Well, we know from observations and from landers which have gone to Venus But the temperature on Venus is not close to that of the Earth, but in fact more than double the the temperature on the surface of the Earth. The mean temperature on the surface of the Earth is about 300 degrees Kelvin. In the case of Venus, it's more like 750 degrees Kelvin. And that's an enormous difference. Well, what's happening here? Clearly, that simple picture I gave you of the sun heating the surface and everything coming into balance does not apply to Venus. And why is that? It's because we have not taken into effect properly the activity of the atmosphere in controlling the temperature. And when you have a massive atmosphere, as you do in Venus, it can have an enormous effect on the temperatures and chemical processes and all the rest in a planet. Well, what's different about Venus? It's got that very deep atmosphere of carbon dioxide, but one other thing, and that is that the temperature at the cloud tops, which is what you're looking at here, is the temperature at a surface which is not the surface of the planet, but a surface which is about 50 kilometers above the surface of Venus. And that makes a big difference. Two things are going on here. One is the carbon dioxide creates a greenhouse effect, about which we've heard a great deal. But the second, about which you don't hear a great deal, is a result of another very simple lesson that we've all learned from the solar system without realizing it. And I don't want to turn off the computer now. And that is a lesson we learn every time we look at a very large mountain. This is Mount Fujiyama in Japan, and you say, oh, I don't see anything special here, but in fact you do. There's not snow everywhere on this mountain, and typically on mountains there isn't snow everywhere. But where is the snow? It's always at the top and not at the bottom. A very simple but profound observation. When you go up a mountain, it gets colder, or when you go down a mountain, it gets warmer. You've never seen snow on the bottom of the mountain and no snow on the top. Well, what's that telling us? It's telling us what I just told you. Go up, it gets colder, come down, it gets warmer. And why is that? It's a result of very basic astrophysics. The fact that as a body moves up and down in a gravitational field, the gravitational field does work on it. So in the case of a mountain, as a parcel of air moves downwards, the gravitational field of the Earth does work on it and introduces energy which causes the molecules to move faster, and we have a higher temperature. And similarly, if air moves upwards, the gravitational field subtracts energy from the parcel of gas and causes the temperature to go down. So if the radiating surface that is in balance with the radiation from the sun is high above the actual surface of the planet, the surface of the planet can be much warmer than the temperature at the the cloud layer, which is in the radiative equilibrium with the light coming from the sun. And it is by this route that the temperature at the cloud level in Venus, which is about as in this room, becomes, as you go 50 kilometers to the surface, 750 degrees. Well, could that be the same thing be happening in other planets? Well, indeed it does. In all of the planets with massive atmospheres in the solar system, whether there are mountains there or not, the temperature goes up as you go down in the atmosphere. So if you were in the atmosphere of Jupiter, and this is an artist's depiction of that atmosphere, as you go down, as one of our probes actually did, you would see the temperature continuously rising until you come to levels where you get ammonia clouds, and you go farther down, and you get ammonia chloride clouds, you go farther down, and finally you reach the point where water clouds are present, and one layer after another of clouds made from different constituents appear. Now, an important point there, in the consideration of life, is that at some level, the temperature is going to be right for liquid water, the basic stuff of life. And indeed, our probes have actually reached that level. Our radio telescopes have seen that level. It's actually at a place in the atmosphere where the pressure is about 1 atmosphere, about as in this room. And if you were there, you would be pretty comfortable, except there's no oxygen, unfortunately. but at least the temperature would be right and there could be liquid water. Could there be life here? I mean, this is a zone where the conditions are right for life. There's lots of organic molecules. There is energy from the sun. There's water. And perhaps there is. And a thing always to keep in mind when you're considering extraterrestrial life is that life is very opportunistic and adaptable. One of the great strengths of life is that it can adapt to many extreme conditions, as we see by finding life in the Arctic oceans, life on the top of Mount Everest, just about everywhere on Earth where life could exist. Now, this is a speculation, but some some astronomers have suggested that indeed life may arise in such a level, and for it to survive, it must continue to be at that altitude. Otherwise, if it goes up, it will freeze. If it goes down, it will get boiled or sterilized. And so it was proposed by none other than Carl Sagan in one of the first papers of this kind ever published in the Astrophysical Journal, that there could well be in the atmospheres of giant planets, and all of them, by the way, have levels where the temperature is suitable for life, creatures which have evolved first as very primitive microbes, have floated at the right altitude, and in time, as a survival mechanism, have developed sort of balloon-like structures which allow them to maintain their altitude and live a happy life. They call them floaters, and this is a picture of what floaters might look like. A speculation, but it's reminding us that the universe is not only stranger than we imagine, it's stranger than we can imagine, and perhaps things like this actually exist. The main point here is that whenever you have a deep atmosphere, you will have a level suitable for life. If there happens to be a mountain there, or a land in this artist's conception, it can be populated, even though the planet is very far from its star, far outside the range of that basic canonical habitable zone I showed you in the very early slides. Well, not only an atmosphere can cause the same effect of providing you a level where the temperatures are right for life, but so can something else. Ice, for example. This may look like a blurry picture, but it's a picture of the satellite Europa of Jupiter. Almost featureless. You can see a few small markings there, but none of the great fields of craters we see on most objects in the solar system. When we look closer, we find that this surface, whose spectrum is that of water ice, this is all frozen ice, is fairly complicated, but in particular, you can see that this ice, this frozen surface, at times is broken up. And you find pieces floating around that used to fit together like pieces of a crossword puzzle. You see a place here that used to match. And what this is telling us is that occasionally the surface of Europa, where the temperature is about 150 below zero Celsius, at times becomes at least slushy. And the surface breaks up and moves around. And we see that in the presence of these icebergs, which are now, they're icebergs, and they're now locked in the frozen slush, which is at the present time solid everywhere. Well, how big is this? This is about 1 kilometer across. So are these. These are all about 1 kilometer. And we have shadows here from which we can deduce the thickness of the ice, of these icebergs. And we know that because about 90% of an iceberg is below the surface and about 10% above. So if we can measure the height, which we can do by measuring these shadows and knowing the geometry of the sun when this picture was taken, we can deduce that these icebergs are in fact about 10 kilometers thick. So that in fact the surface of Europa is about 10 kilometers thick of ice everywhere on the planet. And what's amazing about that is that below that ice cap, there is liquid water. The ice is thick enough to insulate the water beneath it to a sufficient degree that the water beneath is above the freezing point and is liquid, warmed, by the way, by tidal interactions with the planet and from residual heat from the formation of the satellite. I'm sorry, it's a satellite. How thick is the water underneath? We know that from measurements of the mass of Europa, its density, and also some other measurements of electrical currents in the ocean beneath it. It turns out the ocean of Europa is at least 100 kilometers deep, probably 200 kilometers deep. Very deep ocean. The ocean of the Earth on average is 2.5 kilometers deep. On Europa it's 100 kilometers, perhaps 200. In any case, there is more liquid water on Europa than in all the oceans of Earth. There's also organic compounds. They're delivered by meteorites, comet collisions, from black smokers in the water. And there is thermal energy from the tidal forces and tidal distortions of the satellite. And so what we have here is thermal insulation provided, in this case, not by air, but by ice, frozen water. And one of the wonders of all of our universe is that water is one of the few things that expands when it freezes and therefore floats. So the result is when ice is formed on a place like Europa, it does float to the surface and starts to provide an insulating layer. In fact, as you see here, that 10-kilometer of water ice provides about the same thermal insulation as about 100 meters of the standard fiberglass insulation we use when we build houses. Or you could achieve the same thing with 2.5 kilometers of brick or concrete. So for those of you who are real estate speculators, you might contemplate housing developments on Europa, because you could build them on the surface. It's just the roofs are going to be quite thick. They have to be about 100 meters thick in insulation, and they will be warm and cozy inside. And you have certainly an ample source of water, and it would be about the same as living in the Arctic conditions. Well, liquid water, the temperature is very near the freezing point, but it is liquid, and we know on Earth that creatures live in water that is close to the freezing point. In fact, the Arctic Ocean and the oceans around Antarctica are one of the richest areas on Earth when it comes to the amount of animal and plant life. So what might be in the ocean of Europa? We wish we knew, because this is a really serious test case for the ubiquity of life in planets. There really should be some life in the ocean of Europa. And what might it look like? I brought a few things along here which I think, pictures I think, which suggest to you what we might find in some of these places. In the case of Europa, one of my favorites, candidates for life on Europa, fed, by the way, by the energy and nutrients that come out of the deep sea vents, is this. It's called a cone jelly. Any of you ever seen a cone jelly? I don't know if... Hold up your hand. Anybody seen a cone jelly? Oh, that's too bad. Cone jellies, from your name you can tell, they're like a jellyfish, but they're slightly different. The difference is almost trivial. The difference is that the tentacles of a cone jelly do not have toxins in them. They're used simply to shepherd food into the mouth of the cone jelly, which is this opening down here. In true jellyfish, the tentacles all have toxins in them. Cone jellies are extremely beautiful because the combs, I'm sorry, I put the wrong word here, I'm sorry, it's a comb jelly, C-O-M-B, comb jelly. There are combs which are just like hair combs, and they move to propel the creature in the water, and it turns out these combs consist of, in fact, many tufts of hair which resemble a hair comb we use with our comb. And as these move, they act like diffraction gratings and create the very colorful things you see with these. They're about 8 centimeters in size, by the way. They're not small. And this is one of the most common creatures found in the Arctic Ocean of the Earth. You could take this right now and put it in the ocean of Europa, and it would be perfectly happy. And so perhaps something like this actually exists out there, and NASA would love to run a mission to determine if that's true. There are about 100 different species of comb jelly, and they're all very beautiful in the way you see here. Here's another picture of that same species, slightly different lighting effects, and this is what it looks like. Now, that shows us we have an abode of life far outside the canonical habitable zone, in this case brought about by an insulating layer of ice. Another place where this might exist is farther out in the solar system, where the Cassini spacecraft, shown here, has made many important discoveries. One of them, not having to do with life as we know it, was discoveries of the satellite Titan of Saturn. And this is what it looks like. It has an atmosphere whose atmospheric pressure is about the same as here on Earth, but it is mainly nitrogen. It's very much like our atmosphere, except there is no oxygen. There are many hydrocarbons. The atmosphere of Titan is very rich in hydrocarbons and related molecules, which give it this orange cast you see here. And we have sent a probe to it, the Huygens probe, which showed that it has continents, and as you can see, dark areas here which look like lakes. And these are thought to be lakes of hydrocarbons because the temperature here is about 100 degrees Kelvin, which means that all the water is frozen out. But these could very well be lakes of methane, propane, butane, the things you use to heat your house in some cases. Farther out, there's the satellite Iapetus. Actually, not farther out. It's farther out from Saturn. It's a satellite of Saturn, which we learned actually has geysers of water coming off the surface. Here, photographed by the Cassini spacecraft. Geysers of water going hundreds of kilometers above the surface, showing us that there must be liquid water close to the surface here, where again, the surface temperature should be about 150 degrees below 0 Celsius, and yet there is the water. Now, that tells us that something, probably an ice insulating layer, is providing a habitable zone. We don't know how big, even here at the distance of Saturn. At the distance of Saturn, the sunlight is only 1% of what it is on Earth, and so the surface temperatures are very, very cold. But with an insulating layer thick enough, you can have conditions suitable for life. Now, what about the M stars? Those stars which are so common and yet have these problems of the very small habitable zone, possibility of being in synchronous rotation, so they keep one face towards the star, as you see in this artist concept, the other side in the dark. And if it is the case they are rotating at the same rate as they go around their star, it'll be the situation you see here. And what will happen here is the air will heat, it will blow around to the backside where it freezes out, and very quickly all the atmosphere will be frozen out, and it will be unsuitable for life. Well, there are two reasons we know of why that probably isn't the case after all. First, computer modeling of that flow of air I just described to you has shown that if the atmospheric pressure is about 1 atmosphere or higher, there will be enough heat carried to the backside to always keep it above the freezing point of air. And so the air won't freeze out. The other reason is one we've learned as another lesson from the solar system. Our planet Mercury is close enough to the sun that it should keep one face to the sun. And for actually a century or so, it was believed that this was the case. Mercury is very hard to observe because of it's always close to the sun. But it was thought that Mercury kept one face to the sun based on eyeball observations, which turned out, in fact, to be embellished. Now we know from radar observations made at the Arecibo Observatory that Mercury, which you see here, does not keep one face towards the sun, but in fact it does something very strange. it presents opposite faces of the sun every time it comes close to the sun. Now, I'm saying it comes close. You say, what are you talking about? We thought the planets were in circular orbits. Mercury is not in a circular orbit. It is in a not a highly elliptical orbit, but an elliptical orbit such that at times it is much closer to the sun than at other times. And as a result, as it is close to the sun, it is moving very quickly, and tidal torques actually control its rotation, and in time have brought it to a situation where it does what I just described. It keeps one face to the sun, one close pass to the sun, and the other face faces the sun the second time it goes by the sun. So it is not keeping one face to the sun, and this means that eliminates the possibility the atmosphere gets frozen out. It rotates, it has seasons, day-night, just like any other respectable planet. And so that old picture was wrong. As long as the orbit is elliptical enough, and even if it isn't, perhaps the atmospheric effect I just described to you keeps the thing habitable anyway. But what is the ellipticity of Mercury? It's described in a thing called the eccentricity by astronomers, and it's about 0.2. Well, what do we know about the extrasolar planets, of which we know of 347 as of today? About half of them have eccentricities higher than 0.2, and if that rule holds for the planets of M-stars, and of course we don't know that for sure, we never measured the eccentricity of a planet of an M-star, but if it holds, then at least half the M-stars are certainly free of a frozen out atmosphere. Now, that says then that this picture may or may not be true, but in fact it doesn't matter much. Even in the synchronous case, what you have is one point on the star, on the planet that is facing the star. It becomes very hot as you go towards the boundary between night and day. It gets cooler and cooler, and it's a Goldilocks situation where at some zone the temperature will be just right for life, and that's shown in green here. And so in a way, these planets may be, after all, the best possible abodes for life, because they provide us a tremendous range in temperatures, and somewhere conditions will be just right for the origins of life. These would be wonderful places to live. The weather's very predictable. If you're living in the habitable ring on the planet, and you want to have a tropical vacation, you just head towards the pole. It warms up, you can go to the beach and have a little quick vacation in Hawaii. On the other hand, if you want to ski, you just go the other direction, and you don't have to go very far before you will be to a place where conditions are winter conditions all year, totally predictable. So the weather never changes anywhere on such a planet if they actually exist. There's one other problem with M-stars I didn't mention yet, and that is most of them are what are known as flare stars. Occasionally they have eruptions of activity on their surface which cause them to become much brighter, and not by a little bit, not by a few percent, but sometimes they double in brightness for a time which ranges from minutes to hours. And people have wondered if that might not be lethal for life, and would be another reason why M-stars are not suitable for life. Well, you have to remember what I tried to impress on you earlier. Life is opportunistic and adaptable, and we already have creatures on Earth, like the cone jellies, which are quite suitable to live on Mercury. If you want to see one example, I think is a good example, here it is. Here's the turtle. If the star suddenly lights up, the turtle can just pull into its shell and wait out the solar flare light and go on its merry way. In fact, there's another solution to the star flare problem, which is certainly a good one, and that is, if there's bodies of water, all you need to do is jump in the water and go down a few meters, and the water will protect you. You know, the water on Earth, say in the ocean, it does not change from night to day. On Earth, we get full sunlight for 12 hours and no sunlight for 12 hours. That's a bigger change in brightness that occurs in a solar flare on an M star, and yet the temperature of the ocean doesn't really change at all when events like that happen. Also, being beneath the surface of the water guards you against energetic particles which come from solar flares, which can cause radiation damage to creatures, but even a few meters of water protects you from those also. So life on an M star is not hard to evolve. It may be turtle-like. It'll probably be creatures that can, at a moment's notice, jump in the ocean for a while, but that's all it takes to live a long, healthy, and happy life on an M star. So what does that say? Well, the M stars now appear to be in the habitable zone and habitable. There's one other object I want to mention to you, which is probably habitable, and it's a very strange object in that we know that it exists, but we have never seen one, and we may never see one. And these are planets which were born in the process of the formation of a planetary system, but in the process had an unfortunate series of close approaches to other forming planets with such a geometry that the mutual gravitational force accelerated the planets. That's what will always happen when they pass close to one another. Again, it's very simple astrophysics. It's Newton's third law. For every action, there's an equal and opposite reaction. And when two planets pass close to one another, they exert the same force on each other. One planet will get speeded up, and the other will be slowed down. And if you get speeded up 2 or 3 times in a row, you can achieve escape velocity and actually be thrown out of the system. What we've seen in the planetary system we discovered is that this probably happens every time. In fact, when the solar system was formed, there was probably a couple of planets formed that are no longer in the system. They were thrown out. One of them didn't get thrown out. It collided with another one and made what we call the asteroid belt. So we see the evidence of these sort of mutual accelerations and the eventual destruction or ejection which come from them. But perhaps one planet is thrown out of a system every time a new planetary system is formed, and the result is we get planets that have no star. They are moving freely through space, through the galaxy, forever. It's sort of a daunting thought. This is an artist's conception of one of these, a very new planet, because you can see its star in the background in the upper right, and it's still full of volcanic activity because it is so young. And we call these nomads, or rogues, or wanderers. The astronomers have not really arrived at an official name for them yet. So there may be as many of these as there are stars in the Milky Way, And you might ask, why haven't we seen one? Well, if you work out the statistics, in the whole history of mankind, none of these should ever have passed through the solar system. If one did, it would have been seen by the observers, and there were good observers throughout recorded history, but it has never happened. And if you work out the statistics again, it's very surprising. It should happen only very, very rarely. And with almost any star, it will never happen in the whole history of the star. But they are out there. And an astrophysicist, Dave Stevenson at Caltech, has worked out how these will evolve. And what happens is these should develop massive atmospheres, about like Venus, and this will actually keep these such that the surface is warm enough to support life for times of billions of years, even though there is no starlight, no sunlight available to warm them. So these too may be potential abodes of life. It's hard to imagine intelligent life on a place like this, but life, yes. And this is going to be one of the great challenges to astronomy in the future. Let's actually find one of these. They have to be there and see what they're really like. So when we put this all together, we realize that our diagram of where the habitable zone is really extends outwards because of the warming effects of atmospheres, insulating layers of gas and water, and ice, and even beyond the solar system itself, if we take into account the rogue planets. And this means that the number of places where life could occur is very much greater than we used to imagine. Well, will there be life? The experiments in our chemical labs have shown many chemical pathways to the origin of life. All of them use simple molecules which are known to be present in the interstellar gas and the material that makes planets in great abundance. And so it seems it's inevitable that almost every habitable planet will have life on it. That seems one of the things we know, even though we've not seen a second origin yet directly. What about intelligence? There the glass is a little murkier. We know it took 4 billion years to evolve an intelligent species ourselves. And some people argue that there are, in fact, some blockades away, choke points that keep intelligence from developing. On the other hand, the fossil record seems to show that all animals evolve to greater intelligences as time goes on. They're all headed towards becoming intelligent. Just give them enough time and they will make it. In our case, in the case of Earth, there's always one that makes it first. In that case, it was us. And we should not be surprised to look around and find out we're the only intelligent species. This does not indicate, as some paleontologists have claimed, to show that intelligent life is a very rare phenomenon, that you only have one species after 4 billion years. If we waited another billion years, we might have many more up here. For instance, here is one that actually was ahead of us. This is a model of a extinct dinosaur. Its name is Stenonychosaurus inegalis. It stood about our height, weighed about the same as we do. It had binocular vision. Its eyes were placed so it could see as we do. It could grasp things with its forepaws. It was very much like us. And in fact, this one had a much larger brain than most dinosaurs. Most dinosaurs this size, this was a 50-kilogram dinosaur, did have tiny brains the size of a pea. They were really dumb folks. But this one had a brain whose mass was approaching that of a human infant. And it's thought that if this one had had another few million years to evolve, it might have gone from this version to what you see in the foreground here, and there's the ancestor in the background, an upright primate form of reptile with an intelligent brain. This could have been the first intelligent life on Earth, and it might have looked like this. And this is a model made by paleontologists, not speculators, not science fiction writers, but by actual paleontologists who have a sense of how things evolve as time goes on. Well, this one didn't get a chance to make it because 65 million years ago this happened. A 10-kilometer asteroid hit the Earth going 20 kilometers a second, created an enormous explosion which filled the skies of Earth with dust and also with hot embers, which fell all over the Earth after executing orbits halfway around the Earth in some cases, and set the whole Earth on fire. This is the Great Fireball on its way, and here's what a mad dinosaur looks like. This one's really upset at this fireball that's headed for it. The entire Earth caught fire at that time, and then the pall of dust caused the temperatures to plummet on Earth, causing all the vegetation to die. The food chain was broken, and at that time all the large creatures, including the large dinosaurs, perished on the Earth. Few of them survived and became our birds of today. But in fact, what happened here was we did not evolve an intelligent dinosaur. That was cut off by this event. And when the dust had finally settled and the fires had stopped burning, the creatures who had survived all this by hiding in caves and under rocks came crawling out and found they had the Earth all to themselves. And they are us, folks. The primitive mammals of that time, creatures which were about the size of rats and mice, rodents, they made it through the long night, and in time, 65 million years later, they became us. What this says, I think, is that evolution is inevitable everywhere. We know that much for sure. But more than that, that probably the evolution of intelligence is inevitable. So if you put all the things I just said together, it says that maybe once a year in our galaxy, a new intelligent technology-using creature appears. And by the way, once you're intelligent, it's only, in the case of the Earth, it was just a blink in cosmic time before technology developed. So that seems to be something that's inevitable once you have intelligence and the ability to use tools. You may need fire, by the way, because to make really useful tools that will do things that you can detect across the distances which separate the stars, you need metals, and you need to be able to form metals into various things, and that feels like you need fire to do all of that. But what does all this say? There are far more habitable planets and probably inhabited planets than we imagined only a few years ago. We should search for signals from all the stellar types that, where the star lives long enough to evolve an intelligent species. We should give emphasis to M stars. They're no longer ruled out. In fact, it's best to search where most stars are in the beam of your telescope at once, near the plane of our Milky Way galaxy. And don't even avoid observations of empty space, because those rogue planets are out there. And although it seems improbable that there would be intelligent technology using creatures there, again, life is so adaptive and so innovative, it just might be. Well, we can put numbers in all the things I've been describing to you. And if we do, one can make an informed guess, but it's no better than a guess, that there might be 10,000 or of that order civilizations out there using the technology we can detect. How shall we find them? Shall we look for the lights of their cities at night? This is a mosaic of pictures of the Earth at night, and what you see here are the lights of the cities of Earth, and you can easily spot all the main parts of Europe. Paris is easy to spot. Berlin is a little harder, it's right there. Hope you can all find it. And so it goes. You can trace the Trans-Siberian Railway across here, because building the railroad was built first, and then the cities were added later. So they are like beads on a string across the Trans-Siberian to Vladivostok. Well, is this what we should search for? It turns out to detect these lights requires a telescope probably at least 1 kilometer in size and maybe 5 kilometers. Well, we're building big telescopes here, including right here at the Astrophysical Institute in Potsdam, but they're not 1 kilometer in size yet, and that's not in our near future for sure. So this is not what we search for. What else might we search for? Much thought has been given to this over the last 50 years, and when you think about what a detectable signal must be in the way of power, what power is required to create it, how much will it cost you to detect it, it turns out that the thing that is most appealing, always has been, still is to search for radio signals. Radio signals in what we call the microwave band. Now, why is that? It's because we live in a universe which has in it sources of radio emission, radio noise, which in a way jam our radio telescopes and make it so that a signal must be more than a certain strength if you're to be able to detect it. And that noise, which is called cosmic radio noise, is least bright at the frequencies we call microwaves. And we know this and we exploit it without really thinking about it. Those frequencies are used to communicate with spacecraft. They are used in the systems that send televisions to people's homes. And it's all because the radio receivers are looking at a darkest sky, so the little dishes can be the smallest possible size and still work. And you can send signals reliably with the least expenditure in power. We know this, the extraterrestrials will know it. And they will undoubtedly exploit this band of frequencies just as we do. And so for 49 years now, we have been searching for microwave radio signals. The first search, which Dr. Strassmeyer mentioned, was the project in 1960, which occurred not in the state of Virginia, as advertised, but West Virginia. Now, that may seem like a trivial distance to you, difference to you, but if you were in West Virginia, you would be deeply offended by the statement that Dr. Strassmeyer made in the introduction, because the West Virginians consider themselves greatly superior to the peasants, if you will, of Virginia. This is the telescope that was used. It's a 25-meter telescope. Still in use, by the way. It's a very good telescope. These were the people that did the search in a reunion we had some years ago. It was used with what was then a newly invented, very sensitive radio receiver. Today we have much better ones still. But at the time, this search made sense because you could compute with great accuracy how far an antenna this size coupled to that receiver could detect the strongest transmissions we were then making from Earth, and it turned out to be the distance to the nearest stars. We had crossed a threshold where for the first time we could detect other civilizations by detecting their own technology without requiring them to be a super civilization or something like that. All they had to be was to be like us. And it was a fair enough assumption that duplicates of us probably exist somewhere. And a project like this could succeed. In fact, at the time we did this, for all we knew, every star in the sky had planets radiating. This was going to be a very easy thing. Well, it turned out it hasn't been an easy thing. There's been many, many searches since, and so far no signal of extraterrestrial origin has ever been found. In this case, in this so-called Project Ozma, we searched for signals from the two nearest stars, which are single and like our sun. The stars Tau Ceti and Epsilon Eridani, which are both 10 light years from us. We could have detected our strongest signals from those stars. We could only measure a few frequencies because at that time our radio receivers could only monitor one frequency at a time. So we spent 2 months tuning the band, if you will, looking for signals, and we didn't find any. Well, this was the first, and it made other people recognize that this was in fact a reasonable thing scientifically. It was supported by hard data, not by imagining or philosophy. And since that time, there have been about 100 similar searches, searching primarily for radio transmissions in the microwave region, particularly in the frequency band that's near the basic radio frequency of the hydrogen atom. We now have, this is the equipment that was used in that search, just to show you, 4 racks of equipment, all to monitor one channel. Those of you who are old enough may recognize one of these. This is a Hammerland amateur receiver, which is part of the system. This system was all vacuum tubes. Some of you have probably never heard of such a thing, but it was before there were transistors. It was also before there were computers. And believe it or not, there was a time in the history of the Earth when there were no computers. I know that's a surprise to most of the young people here. But it was true, and the data was recorded with a pen and ink recorder, which is right here. And just in case we actually heard something, we had this device here, which some of the old-timers will recognize as a woolen sack tape recorder, which was all set up to record the voices of the extraterrestrials should we have happened on a channel that had voices in it, which didn't happen, unfortunately. Well, it's been 48 years. We've moved on to much larger telescopes. This one is routinely searching for extraterrestrial intelligence signals through the program called SETI at Home, which I think probably some of you work with. It's a way you can search for signals on your own home computer. If you join SETI at Home, which is free, they send you free software, and then when you ask them, they send you what they call a work packet, which is a set of data from the Arecibo radio telescope, which is what this is. And your computer processes it and sends information back to the SETI at Home headquarters. And it just could be that you would be the one to make the detection, the finding of a signal from another world. It hasn't happened yet. There are presently about 200,000 people cooperating in this effort. It has been a very great success. It's a case of distributed computing. It's established a whole genre of computing in which shared computers are used free of charge, typically, to do enormous calculations. It's being used with genome research, with studies of possible protein folding, different things like that. In any case, this is the world's largest radio telescope. It's 300 meters in diameter. Here. This structure up here is 100 meters across. It's the size of the next largest telescope. There are two next largest telescopes, both the same size, both 100 meters. One near Bonn at Effelsberg, and a new one that's at Green Bank, West Virginia, where the first search happened. In this case, the area which captures the radio signals is suspended from these three towers. Each of these is about 150 meters high. This suspended structure here weighs over 1,000 metric tons, and it has a second dome here, which has in it a 20-meter reflector and another smaller reflector to bring the radiation captured by the big dish to a very sharp focus. And this is a closer-up picture of it. One other thing about this is that in it there is a 1 megawatt power radio transmitter, which is used for radar studies, such as the ones who determine the rotation rate of Mercury. And that 1 megawatt signal, when focused into a narrow beam by the big reflector, creates such a power level that to duplicate it without the big reflector would require you to transmit 20 million watts, which is 20 times the total electric power production of the Earth. Very strong signal. It can be detected by a similar instrument anywhere in the Milky Way galaxy. Even at a distance of 100,000 light years, this signal can be detected. And this is what the reflector surface looks like. It's very large. It consists of 38,000 panels, each about the size of a typical dining room table in a house, all put in position to an accuracy of 1 millimeter in order to give high efficiency to the receiving power of the telescope. Now, in recent years, we've recognized that something we had ignored shouldn't be ignored any longer, and that is the possibility that signals are coming from extraterrestrials not just by radio, but perhaps on light waves after all. We had dismissed light waves earlier because the lasers we had couldn't be detected even at the distance of the nearest star, and also the noise associated with photons is much greater than the noise associated with radio photons. And so for many years we thought it was a waste of time to search for optical signals. But now that has changed. It makes sense after all to search for optical and infrared signals after all. What you're looking at here is a huge building. You can get some idea of its scale by these cars and also by these three, well, they're American football fields, but they're about the size of a soccer field, which have been added through the magic of computer graphics to the roof of this building. They're not really there, they're just put there to give you a feel for the scale of this building. Well, what is this building? It's not intended to signal extraterrestrials, but it has in it some technology which makes it feasible and reasonable that there be interstellar communication by way of lasers. This building is what is called the National Ignition Facility. Now you wonder, what's this ignition? What's it getting ignited? What this is one of the major experiments in attempting to find a way to achieve controlled nuclear fusion of hydrogen into helium, as happens in the stars, to provide a clean and abundant source of energy. Now there are experiments like this all over the world. They're all massive, they're very expensive. This one's been costing several $100 US a year, and it's been going on for about 15 years. And it is finally nearing the point, any day now actually, literally, any day now they're ready to try it the first time. I don't know, the whole building may blow up if it really works well, but it's time to try it. This particular one takes the approach of trying to heat a small glass container about 5 millimeters in diameter, 5 millimeters, tiny, which is filled with a mix of isotopes of hydrogen, deuterium, and tritium. And what we know is, because it happens in the sun, is that if that mix is heated to a temperature of more than 1 billion degrees, nuclear fusion will occur, and you'll convert hydrogen to helium, actually producing much more energy per unit mass than we get from our fission nuclear reactors. So this is the game, to make that happen. Well, how do you do that? You have to heat the gases to billions of degrees, and as you can sense, as you do that, the pressure gets really high. The whole thing's going to explode before it ever gets to 1 billion degrees. And the only way to get around that is to heat it so fast that the walls of this glass container, just through inertia, will keep the gas confined long enough that the nuclear fusion will occur before the whole thing explodes. Now, long enough means less than 1/1000th of a second, less than a nanosecond. So what you have to do is to dump enough energy into this little tiny pellet in less than 1/1000th of a second, such that the temperature gets to over 1 billion degrees, and at which point it doesn't matter, everything's going to fuse. But you have to achieve that before the whole thing explodes. Well, how do you do that? You can't just put a blowtorch to it or something like that. The way they're doing this here is to zap the pebble with a very powerful laser and let the laser light heat the gases in the little glass pebble. But it takes an enormous amount of laser light. In fact, this shows you the lasers, actually only half of the lasers, which are used to ignite the hydrogen, ignite in the sense of nuclear fusion, in a pebble, if you will, a little glass sphere 5 millimeters in diameter. Each one of these tubes you see here is part of a very powerful laser. Lasers which have been developed and now work quite well, which, when they flash, produce a flash of light which has a power of 10 to the 15th power watts. That's a petawatt. Some of you will have learned a new word today. Petawatt, that's a word in German too. 10 to the 15th watts, which is 1,000 times the total electric power production of the Earth, comes out of one of these things. But it lasts about a nanosecond, about 1/1000th of a second. Actually, the latest versions produce all this light in 100 nanoseconds. It takes 192 of these to raise the temperature in the little glass bead to the temperature required for nuclear fusion. So this is one bank. There's actually a second bank in the background you can't see here. And in the center is a device with lots of optics and mirrors and things, which focuses all 92 beams on this little tiny target area. And what is there? This is it. It's a little metal cylinder inside which the glass pebble is. You can see it's about the size of the pupil of a human eye. And half the lasers are shooting the light in one side, and the other half in the other side. And there are internal reflections and such as all of the energy in the light ends up in the little glass sphere. And so if all the optics work properly and the beams are properly focused so that they all land on the sphere, it's been calculated that this will result in ignition and nuclear fusion. As I've said, they have finished now all of the construction alignment of this thing, and any day now they're going to try this for the first time. Well, that's an interesting story in itself, but it's of interest to us because these lasers exist. And if you take such a laser and focus its beam with a 10-meter telescope into a narrow beam, like that which comes out of a radio telescope, and we have many 10-meter dishes, or 10-meter class dishes. European Southern Observatory has them, so do many other countries have them now. The beam that comes out is very narrow, and in fact it is so bright that it will outshine its star if it's on the planet of a star, and not by a little bit, by about 1,000 times. So if extraterrestrials want to signal other civilizations, now notice they'll have to want to do this, they can take one of these systems and create flashes of light which are visible all the way across the galaxy, if you will, if dust isn't in the way. And you don't even need to know the wavelength. When I say they outshine the star at all wavelengths. So you don't even need filters, you don't need to know what the wavelength of the light is. It will work. And other places, of course, are trying to make the same thing. Well, that says this just could be happening. There's one very improbable side to it, and that is that creatures have to be wanting to signal. They have to aim this thing at you. They have to know the existence of your planet. They have to aim the beam at you. So it's not like in the radio where you can eavesdrop on other people's radio transmissions. In this case, they have to be intentionally signaling. So perhaps that makes it improbable. But on the other hand, it is very inexpensive to build detection systems. In fact, our eyes could see these flashes if we could respond to a flash of light that lasted a billionth of a second. Unfortunately, we can't. It's too bad. We could all sit out in the yard on a chair and look at the night sky, and eventually we'd see a flash somewhere and get our Nobel Prize. You know, it's a wonderful situation. Unfortunately, our eyes don't have nanosecond time responses. Push that wrong one again. But it is easy to build simple instruments. This is one our group built and has been in use at the Lick Observatory at the University of California for about almost 8 years now. In fact, it was built by a young student. This was her senior thesis. And it uses a 1-meter telescope that was not in much use. It was all very inexpensive. And this device is itself very inexpensive. It only cost a few $1,000s to build. And yet it's quite capable of detecting flashes from stars very far away of the kind I just described to you. It uses a very unusual but interesting technique for detecting signals, which is different from the way we detect signals with any other device. And I think this will be of interest to any of you who are in the signal detection business here. What's in this box you're looking at here? This is the box seen close up. And actually the light comes in a hole in the bottom here, goes in here, and there are a bunch of mirrors in there. This shows you the inside of that box. Here's where the light comes in from the telescope. It goes in here, the light is split by a mirror so that 1/3 of it goes this way, the other 2/3 go this way, and down here there's a mirror which splits that light, so it ends up with 1/3 of the light going this way, and 1/3 of the light this way. And at the end of each of those tubes is a photomultiplier tube of a very great sensitivity and fast time response, nanosecond time response. Those are easy to come by. They've been built particularly for use in nuclear energy experiments. So this is a case where astrophysics is helping us. And so what we have is starlight coming in and being divided along 3 paths, and out of each of these comes a cable, and whenever a photon is intercepted by one of the photomultiplier tubes, a pulse comes out of that cable. Now, why are we doing all this? Why don't we just put all the light into one detector? It's because if you put it all into one detector, you get what we call false positives. You get sudden flashes or pulses of electricity out because cosmic rays hit the detector, or there's a radioactive decay in the glass of the photomultiplier which triggers it, or there's a corona discharge. These things use high voltage. And the end result is if you have only one detector and the first one's built had that, you got false positives all the time, and you never knew which was the real signal and which was something coming from space. In this case, you eliminate the false positives because the light is split 3 ways, goes through 3 detectors, and then the signals out of these 3 cables are compared in a coincidence detector, which looks for the time coincident arrival of several photons. So if 3 photons arrive at once, you win. So in one channel, photons are coming along, almost all of them from the star. Second channel, there are more photons coming at random times. Third channel, random times. But if there's a laser flash, you're going to find in all three channels a photon which is synchronized, and your coincidence detector detects this. And it turns out that with the photon rates we have, that we should get a false positive, where just by coincidence, three photons from the star arrive at the same time, only about once a year, which has been our experience. With two channels, you'd get a false alarm at least once a day. And what we're dealing with here is Poisson statistics, the statistics that describe the timing of the arrival of photons in a system like this, or how things are distributed when you throw salt on a tabletop. In this case, we're not looking for an increase in light intensity. We're looking for a deviation in the statistical arrival times of photons from what is predicted by the Poisson law. A whole new approach to detecting weak signals. In fact, you win with only 3 photons. It's about the faintest signal you can possibly imagine, and yet you can get a conclusive positive result from 3 photons from the fact that they all arrive at the same time. It's been very successful. We've had 1 false alarm in 8 years, which is what we should have. But so far, no true positives. But we will keep searching, and other people are searching. This is easy to do. This is a new setup at Harvard University, where they have a 1.5 meter spherical antenna and they have 64 multiplier tubes. This shows you looking into the telescope. And here's the whole thing. This is the main mirror down here. And up here, there's a mirror here which deflects the light out to the 64 detectors, which aren't here in this picture. And this is being used every night that the skies are clear to search for optical pulses. Now, what about the radio? Let's go back to that. One of the most major projects in SETI is one to build a dedicated telescope to serve radio SETI searches, the microwave searches. And we need this because historically we've always had to observe as guest observers on other people's telescopes. Yet we need a great deal of observing time because we must search perhaps millions of stars before we will succeed. If you accept that 10,000 stars might have civilizations, it means only 1 in 10 million stars has one. So you have to look at 10 million stars before you even have a small chance of success. And that calls for a great deal of observing time. And even at Arecibo, when we could point the telescope, we could only get at best about 20 days a year of observation. And so some years, now it's 10 years ago, we at the SETI Institute decided to build a new system to search for radio signals and build it in a way which was very inexpensive. And that is to, instead of building a single very large telescope, use a large number of very small dishes and connect them together through computer technology so that they duplicate the performance of a very large telescope like Arecibo. And that's what the Allen Telescope Array is. It's a big radio telescope made from small pieces. Doing it this way saves money because the cost of radio telescopes does not go linearly in proportion to the collecting area of the telescope. The bigger you make it, the more it costs per square meter of collecting area. So if you use many small antennas, the total cost of collecting area is very small. You do have to pay a price in the computer electronics to make everything work right. But if you optimize the distribution or the size of the telescope and the cost of connecting the dishes together, you can save perhaps 50% or more in achieving a collecting area of any size you can imagine. And so this project is in progress now. It's a joint partnership between the SETI Institute and the Radio Astronomy Laboratory at the University of California at Berkeley. And this shows you some of the dishes in the manufacturing plant, which is in Idaho, quite a long ways from the observatory. And these are the dishes. They're each 6-meter dishes. They're made by a very special process in which a sheet of aluminum is pressed to the right shape by putting a huge bladder of water on top of it to just press it down by brute force against a mold. And this shows one of the finished reflectors. Of course, it takes more than that. It takes backup structure, things to strengthen it. The reflectors have to be shipped from the manufacturing plant in Idaho to the observatory, which is at Hat Creek, California, a very tiny town, about 20 miles north of the volcano Mount Lass in northern California. The dishes are so large that you have to tilt them up, as you see here, in order that they don't cause accidents on the highway. But when you do this, they're too tall to go under the underpasses, and so they have to be in this rotating mount so that when you have to go under an overpass, you can tilt these up so they're horizontal, and they will go under the overpass, and then you put them back this way and go on your way. And there are the police to make sure that nobody gets hurt in doing this process, and nobody has so far. This is the design. It's a very clever design. There's a 6-meter primary. It is a Gregorian design, meaning there is a secondary reflector down here, which is beyond the focal point of the main reflector, which turns the radiation around back towards the main reflector. And in this way, you can achieve a telescope which is what we call unblocked. There's nothing blocking the path of the rays coming in. Here's how they come in, and you can see this is the path of the rays that eventually come to the focal point, and the whole area through which they pass is never obstructed by anything, and this allows the telescope to be more efficient and also to be less noisy. Now, to make this thing work, you need go back. The radiation is all brought to a focal point, focal area, which is here, and it has been designed so that it can cover a very wide frequency band at any given time, all the way from half a gigahertz up to 11 gigahertz. Gigahertz is 1,000 megahertz. To do that, you need a special, what we call a feed antenna. It's the antenna which captures the radiation. And this is a picture of it. It looks like this. It's got actually 4 sets of fins, 2 are removed. And we want a low noise amplifier, meaning we need temperatures for the first amplifiers of that are that of liquid air. So the first amplifiers are up here. LNA is a low noise amplifier, and we have a refrigerator back here, closed circuit refrigerator, which provides coolant, which cools the low noise amplifier so that you get room temperature, or it's not room temperature, but 80-degree temperatures at the first amplifiers. This is standard practice in radio telescopes. It's just hard to do here because the place where the signal energy is picked off is way up here at this difficult place, and this requires us to actually put the refrigerators in such inside the feed, which turns out to work, much to everybody's surprise. It does not affect the actual electromagnetic performance of the feed itself. The refrigerator was a big problem when these were being built. Nobody made such a small refrigerator, but they do now. And they're made, in fact, for use with mobile phones, mobile phone towers. And so what could have been a very expensive item is really off the shelf, made in large quantities now, and that's what's used in these systems. Telecom. They come from the telephone communication industry. And there's a little problem we call the last millimeter problem, because there you have a short distance where the wiring has to be at room temperature, ambient temperature, and that introduces some noise, and there's been a great struggle to minimize that, and it's pretty well solved. Well, this shows under construction. It's made in a tent, as you see. There's one of the dishes with the backup structure being applied. Once the dish is put together, it's lifted by a crane. Here you see it. And that crane is mobile, and it takes the dish out and puts it on a pedestal. All of this takes about 1 day. And here are 2 finished dishes. And you see the sense of the size here, and you see that there's some happy people because they put all this together. These are recent pictures of finished dishes in place. And the bottom picture is the ATA, the Allen Telescope Array, as it is today with 42 antennas at this point. The ultimate design calls for 350 antennas, which would give it 1 hectare of collecting area. And unfortunately, right now construction has stopped for lack of money, but we're ready to build more dishes as soon as more money appears. This tells you where it is. It's not very useful. Here's an aerial view of the ATA-42, as it's called. You may wonder why the dishes are in such a strange arrangement. And the radio astronomers here will know exactly why that is. It's because these are used in a method called aperture synthesis, in which they are laid out in such a way that when the signals are combined, they can give you a very high resolution, high quality radio image of a piece of the sky. And it will be used for that in addition to searching for SETI signals. This is what the finished antenna should look like. And as again, you see the dishes seem to be spread out almost at random, but they're not. This is all a very clever design which gives a very high quality image. I'm going to show you an animation now of what this will look like. Unfortunately, this animation has gotten slightly corrupted. I don't know what happened, but I'll play it anyway. Anyway, there's some artifacts you will see which maybe look like signals coming in. Maybe they are. What the Allen Telescope Array will look like when it is done. The first 42 dishes are now in full operation. Everything is working properly, and they are being used for a SETI search of the galactic plane, and they're also being used for conventional radio astronomy, particularly to do pulsar observations. It's not the biggest, or won't be the biggest. The biggest is still Arecibo, but other big ones include the dish at Bonn, which unfortunately has never been used for SETI work, and this new dish at Green Bank, where it all started, in West Virginia, which is also a 100-meter dish, the same size as the antenna at Bonn. And as I said, Arecibo is still in full operation, 24 hours a day collecting SETI data for the SETI at Home project. So things are looking up with regard to our search capabilities, but at the same time, at the same time that we're still making more progress. This is a project which just was started in Russia. They had groundbreaking for this project about 2 months ago. It's a project to build a radio telescope which is modeled precisely on the Arecibo design. It's called FAST, which is based on an English name for this project, which is somewhat strange for a Russian project. FAST stands for 500-meter aperture spherical telescope. So it's a spherical telescope like Arecibo, but instead of being 300 meters, it will be 500 meters. It uses an a dish which is not fully in the ground as at Arecibo, but its rim is up at the above the ground. This is the actual outline of the dish. So it's supported by a ring of girders on towers, and it has 6 towers instead of the 3 at Arecibo, plus a new twist, which is they're making the focal point so it's movable. So you see some winches here, and under computer control they're going to move the feet around so as to point the telescope at different parts of the sky. They predict it will only take 3 years to build this, which I find a rather challenging idea. This is what it will look like when it's finished. And I'm sorry, I call this a Russian telescope. It's a Chinese telescope. This is a Chinese telescope being built in southwest China. And here you see it with the feed apparatus suspended from the 6 towers, as the FAST will be when it is completed. So there's a great future ahead. At the same time, there are few dark clouds on the horizon. We've always used our civilization as a benchmark for what might be out there transmitting signals to us. And those signals, our strongest signals, are like the ones that come from the Empire State Building, which is what you see here. These are all the antennas on top of it. 10 or 20 different television stations transmitting typically 1 megawatt each out towards the horizon, so that most of the power actually goes off in space. Here's the same sort of thing at San Francisco. This is probably the most, in the United States, the tower that transmits the most energy. As you can see, it's very, I think it's about 150 meters high. It's got 3 antenna masts on the top of it, and it's got 30 transmitters on it. And up until, well, today still, it is transmitting 20 megawatts of power from the 30 stations that are transmitting from it, 20 megawatts. But in the United States, on June 12th, all the transmitters are being changed to digital transmissions, and the power is going to go down to 6 megawatts. Well, that doesn't sound like a big deal, but to SETI it is, because our benchmark is suddenly getting fainter. And it's a result of improving technology and the transition to digital electronics, which allows you to get away with lower transmitter power. And is that what happens in the rest of the world? Well, we see it not only happening here, we see it happening with the military radars, which are another part of our benchmark. This is a ballistic early morning radar of the United States in Alaska. I don't know if you can read the sign. It says Point Barrow, which is the northernmost point in North America. And this is a picture I took a few months ago. I went up there because I wanted to see if that was a good place to do SETI. And it is, except for this radar, which is transmitting super high power all the time. It was an interesting trip, by the way. I just drove up here and got out and started taking pictures and set up my spectrum analyzer. Nobody seemed to care, which I thought was pretty amazing. But I'm going to show you the spectrum I saw. And to many of you, this will be peculiar, but this is the spectrum seen from the vicinity of that Barrow radar, going from 300 megahertz radio frequency up to 2 gigahertz. And you see one peak here, that's cell phones, or mobile phones, in Barrow, Alaska. No other transmissions, which is good, but this is the radar. And it's, as you can see, its transmission extends over a range of frequencies covering about 50 megahertz. And if you actually watch this, you would see the spectrum is changing all the time. And what's happening here is what is known as a spread spectrum transmission, where the radar is jumping its frequency around, jumping around all the time. And this is a way to keep it from being masked or interfered with by an opposing radar. This same approach is actually used with cell phones and other things. What this says is, though, that even though there's a lot of power coming out of this radar, it's spread out over so much spectrum that it will be very hard to detect at great distance. The last thing I want to show you is the other threat to our paradigm for what we're searching for, and that's the satellites which transmit television to homes on Earth. This is a drawing of one of them. It's an actual satellite known as Galaxy 11. It transmits power to all of North America and most of South America using extremely clever beams, antennas, which beam all that radiation specifically to the areas where the receivers are. Notice the amount of power coming out. You don't have to look at all these figures. C-band is the television channel band. Typical power out is 20 watts. Compare that to the 1,000,000 watts that is typical of our old-fashioned transmitters. Some of them are 75 watts, as you can see. But what's happening here is that instead of transmitting millions of watts to deliver television to homes, we are sending out 20 watts, and all of that is beamed very precisely on the Earth. These are the contours of beam intensity, and you can see that power is going where the receivers are. There's even a finger that reaches out to Hawaii. There's a finger that reaches out to Puerto Rico. And so these are extremely ingenious, but almost all that power is absorbed by the Earth. The actual amount of power going into space is about 1 watt. And that means our planet is on the way to becoming very much quieter, much fainter than it has been for the last 50 years. And that worries us. Very intelligent civilizations will do this just because it's efficient, saves money, but also, very importantly, it allows you to share frequencies. And as we need to do these days because so many people are using things such as mobile phones. So it may be, in the end, we have to go and search for the lights of cities at night and watch for these. They're actually not as bright as you see here. This photo's been enhanced to make the cities look brighter. For those of you who are wondering, here's Berlin. This is a more realistic picture taken from space of the Earth at night. And as you can get a sense, it is going to be very hard and take a lot of effort to see these lights. The one good thing about them is they are there, and they will probably be there for a long, long time. Maybe something else will happen to help us, solar power satellites in space. Maybe there will be colonization of space, and there will need to be communication links and power links between communities in space. Maybe there's a galactic internet, which requires the use of high-powered transmitters to transmit from one stellar system to another. It's a wonderful fantasy. It would certainly help us. It would be nice if it were true, but maybe it is and maybe it isn't. So we are making progress, but there are challenges ahead. And that's my message.